Hi everyone, my name is Calvin McPhail-Snyder, and I'm going to be talking about holonomy invariance of links. Before I get to the math, I want to thank a few people. I'd like to thank Martin and Allison for organizing the Nearly Carbon-Neutral Geometric Topology Conference, and also thank Carmen and Christine for organizing the session on quantum invariance and inviting me to speak. I'm also going to mention that much of the mathematics I will present is due to Khrushchev, Reshetikin, or Blanchet, Gear, Pachar-Morand, and Reshetikin, with contributions by other people as well. I will be talking about some of my independent work building on theirs, but mostly in the second part of this talk, second pair of these two talks. All right, let's talk about some motivation for why you'd want holonomy invariance. So I said it's a quantum holonomy invariant, so I should explain what those adjectives mean. The first one is maybe more standard. If you want to know more about quantum invariance in general, there's other talks too. But what I mean by that is that these are supposed to be parts of topological quantum field theories, and they're constructed using objects called quantum groups. The invariants I'm going to be talking about are definitely from quantum groups. Holonomy is a little bit newer. By that I mean that instead of just an invariant of a topological space X, like a knot or a manifold, it depends on X and this rho, which is a map from the fundamental group of X into some group G. So you have some kind of extra data. And the reason that actually it should be invariant not just of X, but also of the conjugacy class of rho, because if you change the base point in pi1 of X, it's going to conjugate the whole representation, and that's an arbitrary choice. You don't have to depend on that. Sometimes this is called gauge invariance for physics reasons. The term specifically, the reason I'm calling this holonomy comes from the case where G is a Lie group, like in geometric applications. Then it has a Lie algebra fracture G, and rho, the representation rho from pi1 of X to G can equivalently be described by a flat G-valued connection whose holonomy is the map rho. Again, by flat G-valued, I mean little G-valued. Because it's a flat connection, the holonomy map is well-defined, and you get this representation. There is a different terminology and a slightly different viewpoint used by Sharayev and a number of other authors. There's a reference there if you want to read more about that. He wrote a book on them. They call these homotopy quantum field theories, which in principle is a more general object, because what they think of is instead of this category of like spaces and these representations, you have spaces and maps phi into some fixed space y, considered up to homotopy. And the reason that's related to this is that if y is the classifying space of a group, you recover this representation. You could conceivably consider more general things. I'll just mention that if you're interested more in sort of the formalism of how these types of things work, then you should definitely look at their papers because they've developed the formalism better. Just for technical reasons, their invariants only really work for discrete groups, mostly. And so if you want sort of more geometric topology stuff, I think this approach is more interesting. But they're both worth looking at. Okay, so why would you want to do this? I said what it is, but what's the point? Okay, the main reason is, one primary reason is to get better invariance. Lots of geometry is captured by a representation into a Lie group. For example, if you have a hyperbolic 3-manifold, the structure being a hyperbolic 3-manifold is described by a representation rho from pi1 into SL2C. Really PSL2C, but in the context I care about, it always lives, so let's just say SL2C. And the idea is if you use this extra data, you can get a more powerful invariant. This is already a useful approach in geometric topology. If you know about ordinary Alexander polynomials, you might have also heard of twisted Alexander polynomials, which is some kind of upgrade where you include extra data by a representation into a non-abelian group. The Alexander polynomial comes from like an abelian representation. And the latter one is more powerful. There's an interesting survey article. There's some survey articles about this. But twisted Alexander polynomials are useful, and my point is holonomy invariants are in that spirit and should also be useful. Actually, twisted Alexander polynomials really are a quantum holonomy invariant. We'll get to this in the part 2 of these two paired talks. Okay, here's another motivation, which is really a subset of that, but an important subset. So there's something called the volume conjecture due to Khrushchev, also Murakami, and many others. So if you have K, a hyperbolic knot in S3, by which I mean its complement is a hyperbolic 3-manifold of finite volume, and Jn of K is the nth colored Jones polynomial evaluated at a root of unity. So you also need to normalize it differently. So you use a slightly non-standard normalization where the value of all these on the unknot is 1. So these are a sequence of quantum invariants. Because you're evaluating a root of unity, they're complex numbers. Volume conjecture says that the asymptotics of the log of that divided by n gives you the hyperbolic volume of the knot. This is a lot of people are interested in this conjecture because it says that somehow this a priori entirely algebraic invariant, the Jones polynomial, is really saying something deep about hyperbolic geometry. Another reason people are interested is there's a lot of generalizations and conjectures. There's versions for Tribe-Vero. There's various things you do if you if you do different roots of unity, you get different kinds of limits. You can deform a little bit away from roots of unity, and there's Chern-Simons invariants that show up. There's versions of this that are actual theorems, either in special cases or if you have different roots of unity, the right-hand side is actually 0. Really cool stuff. A good overview of some of this is also due to Murakami. It's in the end of these slides. If you look at them online afterward, if you want to know more about that. Anyway, the connection is that these conjectures are a relationship between the asymptotics of quantum invariance and hyperbolic geometry. So the idea is that we can construct a holonomy invariant that's something like a deformation of the colored Jones polynomial by the hyperbolic structure. You could maybe say something about these conjectures. Maybe there's some kind of path through that intermediate construction to prove conjectures like this. Again, I'm not saying this is going to happen immediately, but that's one reason why you'd want to do holonomy invariants. All right. Before I talk about holonomy invariants, I'm going to remind you of how the Reshtick-Tribe construction works in the ordinary, usual quantum invariance case, because I'm going to be modifying it in a second. I just said that. So here's how it works. You need to pick a quasi-triangular Hopf algebra H, for example, a quantum group. That means it's an algebra over like a field with some extra structure, and pick a representation V of it. Because H is a Hopf algebra, V tensor V is also a representation of H. You can't always tensor representations, but you can for Hopf algebras. Similarly, because it's quasi-triangular, there's a map C from V tensor V to itself called the braiding. The reason it's called that is if you put C1 equals C tensor identity and C2 equals identity tensor C, then these satisfy the braid group relations. Also, they're invertible, so they, as you'd expect in a group representation. All right. If you do that, you get a braid group representation as follows. You think about turning a braid, which I'm reading here top to bottom, and turning it into a map. So here I have the braiding, and here I have the a single strand. So I send that to the braiding, tensor the identity. Here I have a strand and the inverse braiding, so send that to the inverse to the identity, tensor the inverse of the braiding. You can also think about these endpoints as being copies of V. So this is V tensor V tensor V, and down here is also V tensor V tensor V. So I've turned this topological braid into a linear map between some vector spaces, or actually not only a linear map, but a H module endomorphism. All right. The point of doing this is that you get this braid group representation. So from the braid group on n strands, I get this map, this homomorphism, script f sub v, that turns braids into endomorphisms of v to the nth tensor power, if I have n strands. Actually, again, not only is it a vector space endomorphism, but it's actually a map of H modules. All right. Now, again, I want link invariants, so to do that I take closures. On the algebra side, taking a closure of a braid is called taking a quantum trace, which is like an algebra construction that generalizes the ordinary trace. In particular, like the trace, it's cyclic, right? Quantum trace of AB equals quantum trace of BA, so it's compatible with the Markov moves on braid closures. In particular, if you take the quantum trace of the image of this functor, you get this complex number, or scalar, f sub v of L, that's actually a link invariant. All right, here's some examples. Actually, technically, some of these are really for framed-oriented links, but you can remove some of those adjectives as you do some stuff. It's not that important for what we're talking about, but if you've heard of the Jones polynomial, that is of this type. So there, your algebra is UQSL2, which is like a quantum group associated to SL2, and if you let V be the two-dimensional irreducible representation of that, then you get the Jones polynomial. If you do SL2 into the n-dimensional irreducible representation, then FV of L is the nth colored Jones polynomial, like I mentioned in the volume conjectures. If you instead use a more complicated quantum group SLN and you pick its n-dimensional irrep, you get the Homfly PT polynomial. Right. Again, here this UQG is a quantum group which is a Q analog of the universal enveloping algebra of G. So it's some kind of object, and that's more complicated, and as you send Q to 1, you get you just get U of G, the usual universal enveloping algebra of Lie algebra. All right, so that was a quick overview of Reshtick-Drive. Let's talk about how it changes for holonomy invariants. Okay, so I should mention this is a Reshtick-Drive or surgery construction. There are also Tribe-Vero or state sum approaches, and also even other things you can do. There's other approaches to quantum invariants and knots in three manifolds. There's not going to be actual surgery in what I'm talking about because I'm only talking about links in S3. If I were going to do this for three manifolds, I'd have to present them as surgery on framed links. That actually can't be done quite yet for the kind of invariants I'm talking about, but if you want a TQFT, you don't just want to talk about links, there are 3-2-1 holonomy TQFTs. I think they're constructed using Triabir or other sort of approaches, but they do exist. I'm not going to get into that, though. I'm just talking about links. Actually, I'm really not going to tell you how to construct a holonomy invariant, because this is supposed to be a relatively short talk. What I'm going to do is sort of say what kind of algebraic machinery you would need to construct one. In part 2 of this, I will discuss in more detail how you could actually do that in the examples I'm interested in. And I should mention that those more details are due to Blanchet, Gear, Patron-Moran, and Reshatikin. If you want to read the paper, it's cited. All right, so there's this problem where we know how to describe links as braid closures, but how do we describe links with this representation of the G, which I'm going to call G links? So again, we start out with a link, that's the closure of a braid. And if you think about it, if you want to understand its group, you can use, say, the Vertinger presentation. Because of the n strands, I can sort of pick out n meridians, one for each strand, and those will generate my knot group. And you can describe a representation of the knot group into G by picking the image of xi for each I. So you just say what group element each meridian goes to, because they're generators. Sometimes I'll abbreviate that by saying that rho of xi is the holonomy around strand I. And the question now is, how do you know rho actually satisfies the relations, right? This can be fairly complicated. In some ways, knot groups are simple, but just like checking whether something satisfies some very complicated set of conjugacy relations can be pretty tricky. So here's a framework for understanding it. If you've ever seen Fox derivatives or Fox calculus, you might be familiar with this, but there's a braid group action on the free group, sort of by conjugation. Maybe a picture is more helpful. So look at one or both of those to see what's going on. The idea is the top strand discontinues its color, and the bottom strand gets conjugated by the top one. If you've seen the Vertinger presentation before, these are exactly the relations. This presentation for a knot diagram, you have one generator for each arc. Notice that this is the same one over the top one because it isn't cut, and at each crossing you get a relation between them given by conjugation. In particular, these give you a presentation. So if L is the closure of beta, you can write a presentation of its knot group as being one generator for each strand, and then the relations are given by this braid group action on the free group. And if you want rho to really be a representation of the knot group, you just have to make sure it satisfies these braid group relations. Because of that, this is helpful for thinking about things in terms of braids. So I wanted to introduce this generalization of braids called G-colored braids. So instead of just a braid, you need a braid on n strands, but you also need this tuple of elements of G, which are sort of like the holonomies around each meridian. And because of that rule I showed you on the last slide, the braids are going to change the colors, right? When I braid G1 over G2, G2 changes. And this is, again, just like applying the relations with the Vertinger presentation. I can think of this as like a morphism, right? So here I'm going from the object G1, comma G2 to the object G1 inverse G2, G1, G1, which I write like this. More generally, you can talk about beta, some braid, being a map from some tuple to some other tuple. And when beta it goes from G1 through ... Gn to itself, then you can take the closure of it, right? You need to make sure that saying that it satisfies the relations is exactly the same thing as saying it's an endomorphism. It goes from a tuple to itself, not some other tuple. All right, so this is an algebraic object called a groupoid, which is a certain kind of category. It's a category where the objects are tuples of elements of G, and the morphisms are braids where that act on the colors by conjugation. So this is what braid generators do, and then you can generalize to braids in the obvious way. So a groupoid is like a group, but composing two morphisms is not always defined. Everything's invertible, but you can't multiply everything. The reason it's called a groupoid is that there's this definition where a group is a category with one object, where all morphisms are invertible. So, right, you have one sort of tautological object, and you can just compose into morphisms. That's group multiplication. In a groupoid, there's more than one object, so you can't necessarily compose things, but everything's still invertible. You can actually think of ordinary braid groups as a groupoid. It's just you take the union of all the braid groups, right? So if you can't compose a two-strand braid and a one-strand braid, whatever one-strand braids. You can't compose a two-strand braid and a three-strand braid, but it still makes sense to consider them the same sort of objects, like say if you wanted to take the tensor product. All right, so to summarize what I've just been saying, here's a comparison chart. Here's the ordinary braid group, or groupoid. It's a category with objects, integer, natural numbers, which keep track of how many strands there are. The morphisms are braids, so like a braid on two strands is morphism from 2 to 2. And if you take closures of braids, you get links in S3. And the point is the G-colored braid groupoid, B of G, is this generalization, where now your objects are tuples of group elements. your morphisms are still braids, but now they act non-trivially on the objects according to that rule I just showed you. And if you take closures of endomorphisms, you get links in S3 with these representations into G of their knot groups. In particular, the point of doing all this is that if I want holonomy invariance, I don't want the ordinary Reschting and triad construction. I want a G-graded version. What I mean by that is I don't want a functor from the braid group void to representations of my Hopf algebra. I want a functor from the G-colored braid group void to representations of my Hopf algebra, which will need extra structure, like more than quasi-triangular. It's got to have this G-grading in it. As an example of what I mean by G-graded, if you've seen this sort of category theory stuff, maybe you know where I'm going with it, but if not, one thing I mean, for example, is that I can't just send each strand of V, right? Because these strands are parameterized by elements of the group now as well. So I need a family of modules, one for each element of G. And the braiding is no longer a map from V tensor V to V tensor V, but it's a map between different isomorphism classes, right? G1 tensor G2 goes to a different thing because the colors get changed when I braid. So what that means is we don't have a braided monoidal category, we have a G-graded braided monoidal category. And here is very briefly one way to get such a category, just as an idea of how to do it. If you want more details about this, you should watch part 2 of this talk. So pick your Hopf algebra H, and you want it to have a big central subalgebra Z naught. So Z naught is central, so it's a commutative Hopf algebra, which means that it's an algebraic group, as in it's the algebra of functions on a group. Closed points of that group G are characters, algebraic maps from Z naught to C. And then a module that sort of lives in degree chi and G, where I'm calling it chi instead of G because I'm thinking of it as a character, is one where the central subalgebra Z naught acts by chi of Z. So just the action factors through that particular of the central subalgebra that gives you the grading factors through that character. One reason we want Z naught to be big is that if H is finite rank over Z naught, so like almost all of H is given by elements of Z naught, then you can just set V sub chi to be H mod the kernel of chi. So it's sort of like taking like the adjoint representation or something. One way to get such a thing is if you have a quantum group, you might know that if you have a quantum group at a root of unity, you get this big central subalgebra, and that's how we're going to get these G-graded categories we want. Again, if you want more details, you should watch part 2 of this talk. All right, if you have any questions, please post them at ncngt.org. I'll be there and happy to talk to you. Alternately, I am stuck at home and I would love to talk to you about mathematics. So if you want to talk about, if you have any questions or want more details, please send me an email and we'll set up a chat. Finally, these slides will be posted at sl2.com if you want to see them afterward. And I'll just show you the references. Again, you should probably look these up online, but here are some papers that I cited in this talk. Thank you.